Step outside on a clear day, and the sky is a brilliant blue, but the sunlight illuminating that sky is actually white light, a completely blended mixture of every color in the visible spectrum. So where exactly do the other colors go? As light passes through a prism, it separates into those individual colors based on their specific wavelengths. In our atmosphere, nitrogen and oxygen molecules act like a massive obstacle course for this incoming light. When sunlight hits them, a process called Rayleigh scattering takes over. These tiny gas molecules easily scatter the shorter, choppy wavelengths, like blue and violet, bouncing them in every direction, while longer, smoother wavelengths like red and yellow pass right through. Here's the paradox. Violet actually has the shortest wavelength of all visible light. It gets scattered the most. Based on the physics of the atmosphere alone, the daytime sky should appear entirely violet. The reason it doesn't comes down to a fragile compromise between solar physics and human biology. First, the sun's emission spectrum is uneven. It naturally pumps out significantly more blue light than violet light. This chart shows the specific sensitivity of the photoreceptor cells, or cones, in the human eye. You can see a prominent peak showing that our eyes are highly tuned to detect blue light, but we are incredibly poor at picking up violet. Our brains process that uneven mixture of scattered blue and violet light and simply default to blue. The sky you see every day is an optical illusion, a quirk of solar radiation and human vision that can easily be disrupted. That illusion breaks down the moment the sun begins to drop toward the horizon. As evening approaches, the geometry of how light hits the Earth changes. As this diagram of the Earth shows, sunlight striking an observer from directly overhead takes a relatively short path. But at the horizon, that light has to cut through up to 38 times more atmospheric mass. Over that massive distance, the short blue and violet wavelengths are completely scattered away into space before they ever reach your eyes. The only light robust enough to survive the journey are the long, lazy wavelengths of red and orange. But atmospheric gas isn't the only thing altering the light. When water vapor condenses into clouds, we introduce a new process, scattering. Because water droplets are significantly larger than gas molecules, they scatter all wavelengths of light equally, which our eyes process as a bright, pure white. And when those clouds gather into a dark gray storm front, they haven't actually changed color. They have simply become so thick and packed with water that they physically block the sunlight from illuminating their bottom layers. The warm, glowing colors of a sunset and the dark, brooding gray of a storm cloud are physical records. They trace the sunlight's arduous journey, revealing the exact density and nature of the obstacles in its path. Sometimes, the sky takes on a bruised, sickly green tint. It's an unsettling color that almost always precedes a massive thunderstorm or tornado. To get this specific color, two rare conditions have to align perfectly. First, the storm usually has to roll in during the late afternoon or evening, utilizing the long red and golden wavelengths of a setting sun. Second, the storm must be a deep cumulonimbus cloud, holding a tremendous payload of suspended liquid water droplets and solid ice hail. Inside that thick cloud, the immense volume of water and ice scatters blue light. When the intense red light from the sunset shines through that blue scattering environment, the storm cloud acts like a massive spectral filter. The resulting light that escapes and hits your eye is green. A green sky is a literal warning sign. It tells you exactly what is suspended above, a violently turbulent system holding enough water and ice to trigger severe, destructive weather. Occasionally, the twilight sky will put on a completely different display, bathing entire continents in a vivid, saturated purple. The culprit is often thousands of miles away. When a volcanic eruption is powerful enough, it can punch right through the weather layer and inject a massive plume directly into the stratosphere. These fine sulfur aerosols settle at extremely high altitudes. Long after the sun has set for an observer on the ground, those microscopic particles are still catching the last rays of sunlight and scattering blue light back down toward Earth. At the exact same time, a layer of stratospheric ozone is acting like a chemical sponge. Through a process called Chappuis absorption, the ozone specifically absorbs yellow and orange wavelengths, removing them from the visible spectrum. The visual equation looks like this. You take the long red light coming from the horizon, add the high-altitude blue light scattered by the volcanic aerosols, and subtract the yellow light absorbed by the ozone. The result is a brilliant, glowing purple. A purple sunset is a visible chemical reaction. It proves that a single localized event, like an erupting volcano, can rewrite the atmospheric filter for the entire hemisphere. The colors stretching across the horizon provide a high-resolution, real-time data visualization of the Earth's atmosphere. Every hue you see is the result of a precise physical equation. It is a constant calculation involving the geometric distance to the sun, the size of suspended particles, and the biological limits of the human eye. These hues are indicators of a shifting environment. Fiery reds mark the sunlight's long journey through the dense lower atmosphere. Bruised greens reveal the threat of hail. And vivid purples are the chemical echoes of a distant volcano. Simply looking up is the most accessible way to instantly witness the invisible physics and chemistry governing our planet.